Hi guys, you're welcome to God Academy. In this lesson, I'll be taking you through power in three-phase circuits. In our previous lesson, I took you through the whole concept of three-phase and you solved a couple of problems. Now, let's delve deeper in the power, finding the power and also handling power in three-phase circuits. If this is the first time you have been on this channel, kindly subscribe to support and please watch this video to the end. How do you find the power in a three-phase circuit? So, as we learned in the previous lesson, a three-phase circuit has two main configurations. We have the delta and we have the star configuration. So now let's derive the power for these two separately, right? So for delta, you know that in a delta configuration, your voltage across your line or your line voltage is always equal to your phase voltage. Then your line and phase current is always equal to your line current over square root of 3. When you come to the star as well, the star is having the phase voltage equals the line voltage over square root of 3, and the line voltage equals to the phase current. So phase current is equal to phase current, right? Yeah. So these are the two things you're supposed to have in mind all the time, which is very necessary. But here we want to understand the power. So generally, even in our single phase, power is equal to the total current times the total voltage. Is that not it? So here, for us to find the apparent power, we have three components of power, right? We have the S, the P, and the Q, where S is the apparent power, P is the active power, this is the reactive power. So to find the value for X, you know that X is simply what? The absolute, right? You find the total current times the total voltage. So whenever you are dealing with three phase, because it is not a single phase, you find the power for a single phase and you multiply that by 3. That is the easiest way we do, okay? So mostly in the balance system. So 3 times P. So in a balance system, you just multiply by 3. So in an unbalanced system, you find separately and add, right? So 3 multiplying what? Um, your product of your V times your what? I. But see something. Your V now, we look out for the line voltage and the line current, not the phase, okay? So look out for the line voltage and the line current. So generally, the formula is given as every power, whether it's delta or star, is generally given as S is equal to square root of 3 multiplying VL multiplying this IL multiplying VL. Okay. So this is the general formula for every configuration. But how do we prove this? So let's see why this is true. So here we can clearly say that if you have your voltage and you want to find the VL, right? So we, as I said, you first find for the phase and multiply by 3. You realize that your V and your VP is the same. So our S is actually equal to VP times. Now our I then becomes IL over root 3. Is that not it? Right. So we are trying to make sure that we are finding for the power for one single phase, right? So VP times what? IP. Let me rather make it systematically. That'll make it work. So good. So I have VP times what? IP. That give me a single power, right? So here you know that my VP is the same as my VL, right? So VL times here to my IP is the same as my IL over root 3. Then this is for a single phase, you multiply it by 3. Now I'm gonna get VL IL. Remember this becomes root 3 over what? 3. Then when I multiply this by this 3 cancel this, gives me root 3 VL IL. And the same happens for the star as well, okay? So here too, you know that S will be equal to VP IP. That is for a single phase. When I multiply this by 3, I get the total power. But my VP here is now VL over root 3. My IP is the same as IL. I'm good to go. This becomes root 3 on root 3 times VL times IL times 3. Then this 3 goes away with this 3, leaving root 3 VL. So this is the power for every configuration. Now let's solve some problems here. So mostly to find the power, we just It's very simple. Okay, for a balanced three-phase circuit, balance means that it is the same phase. Okay, so for a balanced three-phase circuit, what you are going to do is you just take one part. Okay, so you just model one load, you find your current IP, then you also find your phase ZP, and your voltage VP to find all the parameters. I have a couple of questions we're going to solve to understand this. So the first one says a manufacturing plant draws 415 kilovolts amperes from a 2400 volts three-phase line. If the plant's power factor is 0.875 lagging, calculate the impedance of the plant per phase, then the phase angle between the phase voltage and the phase current. This is a simple but a little bit deeper. Don't be scared by the phase, by the impedance and the words. Okay, we just approach it systematically. First of all, you write your parameters down and identify the configuration you are working in. So what configuration are you working in? So first of all, you realize that's a three-phase line, right? So please, when they don't specify whether it's a star or um it is delta, please always go for star. Star is the default. Okay, so if it's not specified, please go for star. So with this one, you know that your line voltage, right, is given. It draws, so supply is always line voltage. Your VL is equal to what? 2400 volts. Now this is our power. That's our power, right? So our power P is, so now this kVA, so it's our power S. So let me clean that. So my power S is equal to 415 kVA. Then what do I have? I have my phi, which is 0.875, my phase difference. And so this is power factor, right? So power factor is cos theta. So let me take this and make it cos theta. I have cos theta is equal to this, as simple as that. The first thing is find the impedance of the plant per phase. The impedance per phase. Okay. The one phase, what is the impedance? When I come to this question, for me to find the impedance per phase, what do I need? I need the voltage per phase and I need the current per phase. Since you are dealing with a star, my voltage can be converted to a phase voltage VP simply by 2400 over square root of 3. Take note of that. And that gives us 1390 volts. Now I need my IP, right? I need my IP because I'm looking for the impedance. To find my IP, imagine I don't have the current, I don't have the resistance. So how do I do? I have a power here, which I knew, you know that there's a power here, is that not it? So my power S here is always equal to IV. Is that not it? And I have my V to be what? Um, this power here is actually the total power, right? So we want to find the phase current. To find the phase current from here, we are simply going to have our S here, which is 41500 over our 2400, which is what? Our line voltage. Because as I told you, the formula for this is IL VL multiplying what? Root 3. Is that not it? So this is where we are using the actual formula we use. So root 3 times IL times VL. So when I make the subject, I get 41500 over 2400, which is our VL, times root 3. And that root 3 is from the formula S is equal to root 3 VLIL. Okay. Then at this point, what's our answer? Our answer is 100 amperes. Now let's finally go to the B part. Sorry, we now have the current. Now we need the Z. So the ZP, which we are looking for, is our VP over our IP. Okay. Since this is a star, our IL will be the same as our IP, so it's still 100. And my VP was 1390 over 100. This gives me 13.9. So this gives me 13.9 ohms. Then the B part is saying that the phase angle between the phase voltage and the phase current. So now I have my power factor. Remember, the phase angle is simply the cos inverse. So my phi equals cos inverse of what? 0.875. And that gives us 29 degrees. Let's check the second problem. It says that, okay, I have it here. So it states that a star connected motor. So is there a way? Oh, okay. I mean, let me share it forward. Okay. So it says a star connected motor is connected to a 4000 volts 3-phase 50 hertz line. The motor produces an output power of 2681 kilowatts at efficiency of 93% and a power factor of 0.9 lagging. Calculate A. The active power absorbed by the motor, B. The reactive power absorbed by the motor, C. The apparent power supplied by the transmission line, and D. The motor line current. So let's solve this nicely. What are our parameters? First of all, it's a star connection. So you highlight that it's a star connection. You take note of the star parameters. Now we have connected to a 4000. So meaning that our VL is equal to what? 4000 volts. That's the first thing. We have our output power kilowatt. That is our P. That is 2681 kilowatts. You have efficiency, which is 93 or 0.93, right? Then we have power factor, PF, equal to 0.9 lagging. So now we have to find the active power absorbed by the motor. To find the active power, remember that absorbed, before it was absorbed by the motor, it was at 100%, and now efficiency made it 93%. So to find a 100% version, if 93 is giving this, what will 100 give? If more, let's divide. So 100 over 93 times what? 2681, right? And that should give us 2883 kilowatts, and that is what our, first of all, power input. Okay, that is our power input, actual power input, and that power input is ideally our active power. So our active power absorbed is simply equal to 2.883 kilowatts. Sorry, that should be megawatt, right? So let me still make it 2883 kilowatts. The B is the reactive, but before you find the reactive, you should find the apparent, right? So now I have my total P. If I want to simply find my apparent, I need the power factor. Remember that P is equal to S cos theta, right? And I have my cos theta as a power factor. So P is always equal to my S times my power factor. So to find my S is equal to what? P over power factor. And that is 2883 K over my power factor, which is 0.9. So what does that give me? So that will simply give me the so that's giving me 3203 kilovolts amperes. And remember that your reactive power is equal to S sine theta, right? Or better still, we can use our R is equal to square root of S squared minus what? P squared. And that gives us square root of 3203 squared minus my P 2883 squared. I've omitted the K because they are equal. So this ends up giving me 1395 kilovolts ampere reactive. Then finally, sorry, we have C, the apparent power. So now that the question is asking for the apparent power, so with the C, our apparent power is simply equal to the 3203 kilovolts amps. Then finally the D, the motor line current. Motor line current. So for the motor line current, remember that power is simply equal to the square root of 3 times V times what? I. or L. Is that not it? So if I want to find my transmission line current, it's simple. I'm going to have my S all over square root of 3 times V odds L. Is that not it? So S is 3203 times 10 to the power 3 all over square root of 3 times my VL is what, 4000, and that gives us 462 amps. And that is all for this section. I'll see you in the next session for unbalanced system.